Welcome to the module. So now we will see the case study on using a temperature sensor as well as a heater circuit in order to control and monitor the temperature on a plant. So now we will see how exactly you use a temperature sensors in order to measure a temperature of an object, and as a result we also require to have a plant in order to understand the exact behavior of a temperature sensor. So for that, to explain you about the case study of making use of temperature sensor as well as a plant, and as we already seen about the data acquisition, by combining all these systems I would like to show you today about controlling the temperature of a plant using transistor as well as data acquisition system as well as a controller which is building in a LabVIEW. So in the last module we have also seen about the data acquisition device, different types of data acquisition devices. One is our normal USB based data acquisition device, and CDAC, compact DAC, so which has multiple channels and multiple slots, so which is attached to the chassis. So the whole idea of this experiment is that we have a temperature sensor. So here if you observe, we have a temperature sensor which is of LM35, which is interface or mounted on a transistor. So this is a power transistor, so 2N3055. So we will be building an electronic circuit in order to heat this transistor to particular temperature. So what temperature? It entirely depends upon the user requirement. So since we are developing a controlling unit, so user has a ability or user has flexibility in order to maintain the temperature on top of this transistor. So but for that we require to have driver circuit or excitation circuit in order to make the transistor to heat. So in order to monitor and in order to control the temperature on the transistor, we have mounted this temperature sensor which is LM35. So this temperature sensor measures what is the amount of heat available and what is the required the set point as decided by the user, and based upon that the control will understand how much amount of input to be given to the plant such that it can maintain or it can able to reach to that particular temperature. So if you recall the complete closed loop control system, as the user intended to understand about system output. So whereas the output in this case is nothing but your temperature, and the temperature is not some kind of electronic unit, we require to have a sensor which converts from temperature to an electronic output. But moreover, sometimes it is necessary to have a signal conditioning circuit. The reason is that in order to match the input units to that of the system input units to that of the output of a signal condition output of a sensor. So in this case, if you clearly observe, we have an error detector which the input is connected to this positive terminal of an error detector, and the negative is connected from the output of sensor as well as signal conditioning circuit if required, such that this particular block will measure the difference between the input as well as the output signal, but both should be in the same units. In this case both are of electronic units. As we are developing the complete system using electronic unit, both should be understandable by the electronic system. So that is the reason we have realized the temperature as well as input in terms of a voltages. So the system input voltage is nothing but what is the amount of voltage required, what is the amount of temperature it is necessary in order to maintain the temperature on the heating plant. For example, like say if I consider the mapping factor or the scaling factor as 1 volt per 100 degree centigrade, 1 volt per 10 degree centigrade, which means that if I provide a system input as 1 volt, the system will understand that the plant should heat it to 10 degree centigrade. So depends upon what is the requirement and what is the amount of heat to be generated on the heater circuit, the user has to be specified at the input side. So based upon that, based upon the current temperature available on the heater, the sensor will understand and gives an electronic output voltage, and which is fed back to the input of the system. As a result, depends upon how much amount of input signal is available and what is the output temperature, it will measure the error. this error will be given as an input to the controller. So generally you can use on-off controller, P controller, PI controller, or neural network based or fuzzy logic based, any kind of a controller which will understand the error component and will generate a manipulated variable such that it maintain or it controls the temperature on the plant. The temperature on the plant is equivalent to the set temperature by the user. But unfortunately, sometimes whatever the manipulated variable given by the controller may drive the plant, or sometimes it may not. So in order to make compatibility with respect to the output of the controller to the heating plant, we require to develop a driver circuit. So in this case, as I have already told, we are generating a temperature on a transistor. So we require, and whereas the controller which is nothing but LabVIEW plus data acquisition device, in this case the data acquisition device cannot provide you enough current in order to heat the transistor to the required temperature. As a result, we require to build a triggering circuit or driver circuit which can act as an input from the controller and takes the power directly from the power supply and allows the plant to heat to certain temperature. So for that we will be using this particular circuit where it uses an operational amplifier. It need not to be TL082, it can go with 741 general purpose operational amplifier too, and this is the 2N3055 which we have seen just previously, which contains a temperature sensor which is mounted on it, and it is powered with a plus 15 volts. The base of the transistor is connected to the output of operational amplifier using a current limiting resistor so that it will not damage the transistor, and to the negative feedback we have connected the emitter of the transistor. As a result, if you recall the complete working of the circuit, it maintain the output voltage across this R1 resistor to be same as the voltage connected at positive terminal. This is because of virtual concept. So as the operational amplifier virtual concept says that the difference between both the terminals should be always equal to 0. Since the input is positive terminal is connected to 0.5, it tries to maintain the negative terminal also be at 0.5. As a result, the drop across R1 will be 0.5. So since the R1 is known to us, which is of 0.1 ohm 10 watt resistor, and the voltage connected is of 0.5 volts. So the current flowing through the emitter of this transistor would be somewhere around 0.5 divided by 0.1, 5 amps. So as a result, out of 15 volts, so since the emitter is connected with R1 resistor, the emitter current will be 5 amps, and based upon the principles of transistor, we know that the collector current and the emitter current is approximately the same, which is a proportional with a proportionality constant as alpha. As a result, the emitter the collector current will also be approximately of 5 amps. But when we see the input is connected with 15 volts, but the drop across this resistor is of 0.5, but what about the rest of 14.5 volts? So that 14.5 volts as well as the current flowing through this transistor will generate heat on top of the transistor, and this will be the heat which is generated on top of a transistor will be measured using the sensor and fed back as an input to the error detector. So as a result, it generates an error and it continues the understanding based upon the intelligence that we created on the controller. It will try to understand how much amount of input voltage to be provided at the input side of the driver circuit. So now if you carefully look into the working of the circuit, the current flowing through this R1 resistor entirely depends upon the voltage drop which is being generated across this R1 resistor, and moreover the voltage drop across this R1 resistor is due to the voltage connected at the positive terminal of an operational amplifier. Higher the voltage, higher the drop across the R1 resistor, as a result higher the current flow through this, but lower the voltages, lower current, so lower heat dissipation across the transistor. So the complete working, as we have already seen, now we will see how to build the controller logic using LabVIEW and how could interface the driver circuit, the plant as well as the sensor the data acquisition device and how can we understand the working of different controllers is the today's task. So, in LabVIEW I will be developing error detector, and the system input is also be controlled by using LabVIEW user inputs, whereas the controller can also be realized inside the LabVIEW environment, whereas the plant as well as the sensor will be externally connected to the data acquisition system, where it acquires the data and displays on the LabVIEW device. Now, when we look into the LabVIEW, so it contains front panel as well as a block diagram. So, it is similar to that of our day to day life systems what we see in our laboratories too. So, the front panel really is similar to that of our function generator or power supplies, where user will have user can have access only to either the knobs or can visualize what exactly happening, the buttons, chart. If it is an oscilloscope, it's like having a graph or chart on the front panel, but the complete logic will be sit inside the block diagram. So, during the operation the user will not have any access on the block diagram, but user can manipulate things in front panel. So, it is similar, the structure of LabVIEW is also similar to that of our real time environment. So, even in case of our normal systems, if you observe, the electronic modules will be sit inside the system. When the system is under running condition or operation, we do not have any access to manipulate or modify any items, but user can change the knobs to understand or in order to create a cursors inside a graph. So, everything can be controlled by the user end. So, the same way even the LabVIEW platform looks in the similar way. So, now what we require, we have to connect our controller unit, one is error detector as well as other one is controller in a LabVIEW environment, then we have to interface it to the real world. Now, if you see, so as our application is similar to temperature monitoring application, I will take one input, the set point. So, this I will rename it as set point. So, let me zoom in. So, I am changing it to control. So, I will also provide unit display as well as digital display. So, that whatever the required temperature that the user require can be set at this point. Now, we also require to have the output system. So, now I am generating the temperature output, actual temperature. So, this is a set point, what is the exact temperature that the system has to be, whereas this is an actual temperature, what is the temperature right now the system has. And so, this should be an indicator. So, I will change it to indicator. Now, if you observe, if I directly connect from here to here and when I run the process, we can see that, say for example 100, automatically the temperature on the indicator will also change. So, there is a difference between a control and an indicator. So, the user can only have an access in order to change any parameter, but whereas the indicator can only display. But the intention was not to directly connect it here, our intention was to develop an logic algorithm which can monitor and control the temperature on the plant. So, for that, so what I will do is that I will go with a control system toolbox, so which is nothing but control and simulation toolbox. So, where I will create a control loop, so this is a control and simulation loop, and in this I have to build an error. So, first step, in our circuit is we have to build an error detector. So, I will build an error detector now. So, for that I will take summation block, which is already available in signal arithmetic of control and simulation toolbox. So, I just rename this to error amplifier because this the operation of the summer in this case is similar to that of actually it is a difference amplifier, it is similar to that of our error amplifier. So, not to confuse I will change it to error amplifier or error detector. So, one input to this error detector is connected with a set point and another input, the negative terminal, should be from the sensor, but in this case the sensor is externally connected. So, we require to create a data acquisition modules in order to acquire the data from the real world. So, for that what I will do is that I will create a measurement IO, I will create the data acquisition modules in order to acquire the data. So, for that I will create new VI. So, in this case I will go to NI, I will create a channel and then I have to read the channel, then I should display it, but which channel. So, for that I will create physical channel, create, change to control, so I will rename this as sensor channel. So, if you observe, the system has been connected with two different modules, one is my DAC, one is our CDAC, other one is USB DAC. So, in order to understand about the configurations of USB DAC as well as CDAC, what we can do is that, as we have already seen in the last time, we can go to NIMAX, which is a measurement and automation explorer. So, where we can have the complete access of the particular data acquisition modules connected to the PC. So, in this case if I go to devices and interfaces, here we can see one is USB DAC, which is named as day 1, and other one, when I look into the network devices, we have CDAC 9189, which is also named as CDAC 9189 1D0882. So, we will be using these two. So, in this case, so I will be using since it is for the acquisition, I will be going with CDAC module 2. So, now I can see what are all the modules has been connected into this module. So, we will be accessing NI 9207 in order to acquire the data from sensor. So, in NI which is a module 8 9207, if you look into the pinouts of this particular device, so this is the particular system what we have. The first set of if you see here, we have AI0 to AI7, which can make differential output, and it can also work for both the acquisition of analog signal as well as generating acquisition of current, as well as it can also be used as a power supply, but it cannot provide enough current or enough voltage in order to drive any circuit. But since our intention was to acquire the data from the sensor, we will be connecting the sensor to AI0 plus and AI0 minus, which will be in voltage format. So what I will do is that I will create a sensor channel with CDAC module 8. So, CDAC 9189 mod 8, but AI0. So, this one just data operations make current value default, and our intention was to acquire analog data. So, analog voltage. So, as this particular block can be also used for acquiring analog input as well as analog current as well as voltage, I will be selecting it as a voltage. Then So, the next step is creating an error, create control, so that it gives an indication if in case if any particular block throws an error without any problem during the execution. So, custom scale task in and task code will be connected here. So, error out I require change to indicator and replacing with this one, and this particular block is my data. So, create indicator. So, I will be creating a pinout for this. So, this is sensor channel in, this is error in, whereas this one is error out, and this particular pinout will be connected to the data. So, which data is this? Sensor data, temperature sensor output. Now, let me save this file, save as. So, I am going with, I will be replacing everything in a desktop. I will create a folder, temperature acquire. So, I save this file, then I will be calling this file, since it is I will be using the same file as sub-vi. So, just for our sake of interest, we can also change the edit the icons as well. So, I will replace this with this one. Let me delete this part, I replaced. So, this particular block I will replace with temperature sensing, whereas this one is AI. So, since it is a temperature sensing value, we can using some graphics we can also indicate the functionality of this particular block. So, say temperature. So, here we can see different types of blocks available. So, which will not fit in this case. I will take this, so I will write a text showing as C. Okay. Now, let me save. So, here we can see, but whatever the output that we get, so we have to provide the channel. So, create control, I am creating a control. So, since the default is this particular channel, it will automatically set. Now, what is the mapping factor that we consider for the set point? If you recall, the mapping factor that we use of 1 volt per 10 degrees centigrade, meaning if I provide input as 1 volt, which means that the system will understand the system has to operate at a temperature of 10 degrees centigrade, or control at the system should have a temperature of 10 degree. But when you look into the sensor LM35, the sensitivity of sensor is 10 millivolt per degree centigrade. So, in order to map the scaling factor, in order to match the units of the output from the sensor to the set point, we have to provide a gain of 100 such that both will have same mapping factor, which is 1 volt per 10 degrees centigrade. So, for that what I will do is that I will take a multiplier, I will multiply the output of the sensor, the output of a sensor data with 100. So, let me create a constant dBl constant, so which is of 100. Then this I will be connecting it here, so that the whatever the data output that we are getting will have the same units as the input. Now what we have to do, the output of this error detector has to be interfaced to a controller, right. Now so as we have discussed, we can design on off controller, we can design P controller, we can design PI controller as well as PID controller. In this case I will go with either P, PI controllers, but I will also show you how can I build a PID controller using this. So just we will go to control and simulation toolbox once again, and then we will go to simulation. Here if you see, we have different types of signal arithmetics where we can create a gain, and since we require P plus I plus D in order to construct a PID controller, as well as we also require a differentiator as well as an integrator. So we can go to control linear systems, and we can take integrator as well as a derivative component here, and the output of the error detector, which is nothing but an output which measures the difference between the set point and the feedback signal, output signal. So by connecting the output of error to the input of all the gains, and by adding an adder circuit, we can realize the either P or PI or PID controller. So provided, depends upon what kind of a controller that we are realizing, other particular gains should make it as 0. So we also required another arithmetic. I will copy and paste this particular error detector, but in this case we require 4 inputs, and this should also be positive, or I will make in this way, this is positive, this is okay. So such that this I say adder, so P connected here and this should be connected here. But the problem comes here is how do we manipulate the gain from the front panel. So for that what we can do is that we can double click on the gain. Instead of taking parameter source from dialog blocks, we can make it as a terminal, so that see P underscore gain, so that we can create a control at this point silver, okay. I will go with numeric horizontal point slider. I will also create a digital display, so that easy to understand what is the value of a P gain, but this should be P gain. So this particular block I can connect it to the input terminal. Similarly even for I gain and even for D gain. So if you make P gain as greater than 0 and I gain and D gain as 0 0, that means the particular controller that we are realizing is of PID controller, P controller. But if you make only P gain as high and I gain some value but D gain as 0, that means that particular controller is PI controller. So with this we can understand how can we easily we can create P as well as PI as well as simple I, or combination of P and I, or combination of P and I and D. But we cannot use a simple D controller, because when the error is a constant, the derivative gain will become 0. So which the controller will confuse us what the output given by the controller will be always 0, right. So what we have done, we have created a complete system with error detector, set point connecting, as well as the sensor data with a signal conditioning system. So this is set point. The user can provide this is like comments the required temperature for the plant to operate, and whereas sensor data with amplification, temperature sensor data with amplification, and whatever we get is error output P plus I plus D controller realization and the output will be manipulated variable, but this manipulated variable should be given as an input to driver circuit. So, but right now whatever the system it is being generated will be the data acquisition device will not understand how much amount of voltage to be given. So, this has to be interfaced to the data acquisition by using analog output modules from measurement IO. So, which is similar to that of what we have created for acquiring the signal from the sensor. So, in order to do that, what I will do is that I will create another LabVIEW file. I will open another LabVIEW file with containing the data about from which particular channel the manipulated variable has to be given to the real world. So, since we require analog output voltage, so which is nothing but a generation. So, I just created a channel, I will be creating a channel control. So, this particular channel will provide the manipulated variable as output to the real world. So, from which channel we have to provide? So, we can use DAV 1. So, from the NAMAX, if you observe, we have seen different types of devices which is connected, which is NI USB 6008 as well as CDAC 9189. So, for acquiring the data from the sensor we are using CDAC, whereas for generating the signal to the real world we will be using 6008. It is not meaning that the same device cannot be used, but if we have connected with the same analog output module to the same data acquisition device, even the same chassis can able to generate as well as acquire the analog voltage signals. But since right now I have not connected with the analog output and we also have the USB data acquisition device, I plan to show you the acquiring using CDAC as well as generating using another data acquisition device which is USB device. Even similarly, even with USB device it is able to acquire as well as generate the same signals. So, when you look into the pinout, we have different types of connections here. So, when we look into that one side, it has a total of 16 analog pins on one side, whereas another 16 pins on the other side. So, one side they written with the name of analog, other one has written with the name of digital, which means that whatever the analog that we require can be connected at this side and digital blocks can be connected at this side, and this is connected to the to the PC using USB cable. Now, when we look into the pinouts of this particular device, we can see the pinout configuration of complete device. So, it contains the first terminal is ground, it contains a total of 8 analog channels. Out of 8, 4 channels can be used as differential input, whereas remaining 8 can be used either a differential used as single ended input. So, in this case I will be using AI0 plus as well as AI0 minus such that the AI0 pin the output since we require to generate an output signal, we have to go AI0O. So, AI indicates analog input, AO indicates analog output. So, that means that it not only having analog input, it can also generate a signal by using 2 channels which are at 14th pin and 15th pin. And on the other side if you see, which is from 17th to 32 pin, it has a total of 8 digital channels. Along with that, it also has power supply to the sensor, which is 5 volts, as well as it also has voltage which can generate up to generate a voltage of 2.5 volts and ground. So that means the sensor, the voltage required for the sensor can be easily powered by using this 5 volts too. Now, so what I will be doing is that, since we understood the DAVN can support for analog output generation, I am using the USB DAC, which is named as J1 in the PC, will be used to generate it. But so in order to generate it, the output from the manipulated variable has to be right to this. So I have created a task with the which contains this physical channel, then I will create error control and the output of this will be connected here, then create indicator. So the detailed explanation of this particular block can be easily seen here by pressing Ctrl H or going to the help window. The detailed help, this is just a summary, and if you require the complete detailed help of this particular block, you can click on the detailed help. Here we can, it gives you the information about the module what we have selected in LabVIEW. So in this case, if you see, the bold indicates the compulsory terminals to be connected, whereas the bold is, it is required, until unless these particular terminals are connected, the device cannot operate, the device cannot work. Whereas the hidden text, if you see, it indicates it's recommended or optional, whereas other sets which does not have, which is not even bolded as well as which is not even hidden, these are nothing but recommended. So even if you connect, it will work, even if you do not connect, it will work. But when you see that, it does not mean that it will not pass any data, but default it contains some particular value. So for example, say when we consider auto start specifies this VI automatically start the task if you did not explicitly start it with DAQMX start TI. So in case, if even if you connect, it will work, even if you do not connect, it will work, but if you do not connect it, it will consider some default settings which is already available, and it will work like that. So since we require to generate analog output single sample DBL way, so create constant true, then data. So I have to write the data. So what I will do is that I will create control. So whatever the data that I pass at this particular block, the same will be generated at the AO terminal which we have specified here in the USB DAC. So let me rearrange. So this is output data. Now just data operation, make current value default. So similar to the previous one, I will also give a ping connection, so that the same VI can be used as a sub VI in another program. And let me go to layers, delete it, create a template with, since it is sub VI, and this is for manipulated variable. So which is indication of writing a data. So I have generated it. So this is manipulated variable generate. Now so this is also done, but this has to be interfaced to this has to be called in the main VI. Now I will go to, I will create a sub VI, I will select a VI, so which is MV generate, I connected it here. So, the output whatever it is being generated has to be sent to, oops. So, this is output data. So, this is an input. So, which should be connected at this point, yeah, control S. So, this I am connected here, but we cannot directly connect. The reason is that since it is a simulation, the system can even provide infinite amount of data as an output, but in reality the data acquisition device cannot provide no very higher magnitudes. So, each device has limitations with respect to the operating voltages as well as current. So, similarly even with the USB devices, the output voltage it can generate is of 0 to 5 volts. So, since the simulation can go up to more than 5 volts even with the positive as well as negative, in order to not to have any conflict between the values, we can create some kind of a threshold such that if the input voltage is greater than particular value, send the output as a maximum, right. And moreover, if you recall the driver circuit, the maximum voltage, in order to not to acquire more amount of current, not to damaging the circuit. So, we can restrict the input voltage connected to the driver should be not more than 1 volt. So, that by creating some logical icons here, logic saying that if the input voltage is greater than 1 volt, pass the maximum voltage here, such that the generated output voltage will not be greater than 1 volt, which both the driver circuit as well as the plant the data acquisition device will be in a safe zone. So, let me add all the required components. So, now if you see the complete complete system is connected. So, I have added with the logic whichever I told you. So, that when the input voltage is greater than 5 volts, since the data acquisition module USB data acquisition module cannot generate a voltage more than 5 volts as well as less than 0 volt. So, any voltage which shows more than 5 volts will be shown with 5 volts. Similarly, any voltage lower than 0 volts will be shown as 0 volts. That particular logic has been designed, and moreover, if the simulation generates more than 5 volts, the system will automatically switches off. Moreover, any stop button pressed from the output side of from the front panel, even the system will switches off. Similarly, I have also added the display unit in order to visualize both the input as well as an output signals in the same graph, so that it is understand how much time it is taking the system to respond with respect to the controller could able to reach the temperature on the plant to the required set point, right. So, with this the software side we have done. Now, we have to make the connections in the circuit board.